Ready, Misha? So we just watched a video of no normal force. Pretty cool. Another force we want to talk about is air resistance. Air resistance is the force of air molecules bumping into an object that's moving through the air. And here is the key that you want to underline. The force of air resistance always has a direction opposite to the motion of the object. Which way is air resistance? Which way is the object moving? It's in the other direction. Okay? So we can draw free body diagrams for the following three situations. Situation A is the ball being thrown. That's while it's in my hand. In fact, look up. I'm talking about this part right here. Situation B is once the ball has left my hand and it's on the way up. Situation C is after it's on the way up when it's coming back down. B, C. Oh, and A while I threw it. With me? I'm going to zoom in to diagram A. And I'm going to be a bit sloppy. I got room right here. What are the forces acting on ball A, on situation A, right there? Get the obvious one. Which way? Down. What else? Now, why can't that be correct? If that was the correct free body diagram, which way would that ball have to be accelerating while it was in my hand? Down. Is it accelerating down? Which way is it accelerating when it's in my hand? Up. So there has to be a bigger arrow pointing which way? So I would look for this. I always exaggerate it so it's obvious. What force is that? Give it a name. How about F throw, F hand, F. Let's call it F hand. If you called it F throw, fine. I don't know really what to call it. I just know it's there. And I know it's bigger. Is that okay? How do I know it's bigger? It's not because the ball's traveling up. Watch. The ball just traveled up. But I guarantee you my F hand was not bigger than gravity. It's not that the ball was traveling up. Is a key word. It starts with letter A. It's accelerating up. Watch. It's not accelerating up. I was going at a constant speed. Does the ball leave my hand? I have to put a force bigger than mg. I've got to accelerate it up. Some deep thinking going here. All right. Now, it's left my hand. On the way up, I'm going to do that right here. What are the forces acting on it? Get the obvious one. Gravity. And now that it's left my hand, what we're going to start to say today is it's vulnerable to air resistance. Which way is air resistance going to be pointing? In the opposite direction of the motion. Which way is the ball? Here we, by the way, Brian, here we are talking about which way it's traveling. Which direction is the ball traveling? Up. So which way is air resistance? Down. I already have one force down. I don't like to overlap my arrows. If I have two forces in the same direction, I typically just write the second arrow off to the side a little bit. And I'll call that F air. If you want the fancy term, we call it drag, but F air. I'm pretty sure air resistance is smaller than gravity, so I drew the arrow shorter. How do you know, Mr. Dewick? Patience. Those are the two forces acting in situation B. Situation C. Now it's on the way down. What are the forces acting on it? Get the obvious one. Gravity, which way? Down. Now there's also still going to be air resistance. But which way is air resistance going to be acting here? And this is how I know that air resistance must be smaller than gravity, because if it was bigger than gravity, it would be accelerating up in this situation, not accelerating down. And I know when you throw something into the air, it does come back down. So if air resistance is smaller in situation C, it's got to be smaller than mg in situation B. Is that clever? Yes? So here are my three free body diagrams. In the first situation, now I always have somebody say, Mr. Dewick, isn't there air resistance in situation A? And if you put that on there, I wouldn't be offended. I think I'm kind of arguing that my hand is protecting the ball and covering it from air resistance before I throw it. It's kind of a vague situation. I wouldn't really ask you one this loosey-goosey. I'd phrase it much more carefully on a test. Example 2. In example 1b, the middle diagram, how the heck can the ball be going up if all the forces on it are acting down? Ooh. Candy, if somebody can give me this. I've dropped the hints today and last class. See if someone can put this all together. How is it possible for the ball to be going up when all the forces are pointing down? Yeah. So?
And it's bigger than the forces that are acting down.
Dylan.
Forces are acceleration, and it has a spreading velocity going up.
Keep going. What?
The force is the velocity. So
Force affects acceleration. Don't confuse V and A. They're not the same. Now, if you keep that force up long enough, eventually your velocity and your acceleration will match the same direction. That's why the ball comes back down. But just because you have a velocity in one direction does not mean you can't be accelerating in the other. It's what you do every time you hit the brakes in a car. What direction is your velocity? Forward. What direction is your acceleration when you hit the brakes? It's backward. Yeah. Force affects acceleration, which affects velocity, but force is independent of acceleration. Is independent of velocity. Eventually, velocity will fall into line. Has Dylan convinced you? That's a good explanation. Okay. Example 3. If the falling ball in example 1c is speeding up, write a force equation. Okay. I'm going to scroll down. You all have the picture still on your piece of paper? Yes? So look at 1c. Look at the free body diagram. Who's winning? Who's winning? Really? Yeah. Who's losing? Is air in the opposite direction in C? Yeah, yeah. So it's going to look like this. mg minus F air. What does winner minus loser always equal? Yeah. So now we're at a point, Cole, where I can start to calculate the force of air resistance. I did a big rant earlier this year where I said, when I showed you the video of me jumping out of an airplane, where I said air resistance is a really tricky force because it varies. The faster you go, the bigger it gets. But if I can measure the acceleration of an object, I can figure out how big air resistance must be at that point in time. Is that all right? Next page. Example 4. A parachutist free falls for a time and then opens a parachute. His new upward acceleration is now 1.5 meters per second squared, since he's slowing down while still having a downwards velocity. A says draw an FBD. What does FBD stand for? Let's do that right here. There's the parachutist. What are the forces acting on this parachutist? Get the obvious one. Gravity? Which way? Is there a normal force? Are we on a surface? There's no normal force. What else? Which way is this parachutist accelerating? Read the question carefully. So which way is he accelerating? Which way is the bigger arrow have to be pointing? Which way is he accelerating? Which way does the bigger arrow have to be pointing? Has to be. There has to be a force up that's bigger than mg. What force is that? Oh, the parachute. Yeah, what have we called that force today? We've given it a special name. Drag or air resistance. I'll call it F air again, but if you called it F drag, I'd be fine with that too. Have we written our free body diagram? Yep. Jacqueline, what does B want me to do? Who's winning? Who's losing? What does winner minus loser always equal? There's my force equation. Cool. Joel, what does C want me to find?
Find the force of air resistance.
Oh. How would I get F air by itself? What will I do with that minus mg? Really? Nice. So I don't need to memorize this equation. I can derive it from the free body diagram and then just go winner minus loser, which I think is a better way than trying to memorize every single nutso equation out there. Okay, so for part C, you're telling me air resistance is equal to MA plus mg, or mg plus MA? Cool. Joel, did they give me M? Read carefully. Oh, I love that. You saw the kilograms and went, duh. Good. We're getting our unit trick. This is why I said it's worth memorizing units. Good. Did they give me the acceleration?
Yeah.
What? Do I need to worry about positive or negative? I took care of that when I came up with my free body diagram and my winner minus loser statement. I took care of all that for me. Then there's a plus sign, then 90. Joel, G?
Yeah.
What is G? You know this. It's last block. You know this. Yes, thank you. Okay, how big is air resistance? Can I do this in my head? It's going to be 90 times 10.3. So it's going to be 900 plus... Is it 927? 917? Really? 917? Is that right? 1,000 and what? 1,017. I forgot. I moved a decimal over wrong. 1,017. Thank you. By the way, in this same situation, hint, hint, I like this question, like this question, like this question. What else could I do? Joel, instead of giving you the acceleration and saying find the air resistance, I could tell you how big air resistance was, and I could say find the acceleration. How would I get the A by itself? Divide the M. Divide the whole side, the whole other side by M. Done. Again, do I need to memorize that equation? No, please don't. I'm teaching you how you can derive this. Now, the force of air resistance actually is not a constant value. It gets larger as speed increases. A falling object will eventually reach the point where the force of air resistance equals the weight of the object, and then your free body diagram has gravity down and air resistance up as the same length arrows. If the arrows are the same length, that means the forces are, I'm looking for a word that begins letter B, balanced, and so that means your acceleration is 0. Does that mean you're stopped? No, your acceleration is 0, not your velocity. Your velocity is now going at a constant speed. We have a fancy name for that. We call it terminal velocity. Put pencils down, look up. So that's air resistance. I'm going to do one more. I think this is the last question. Yes. And then I can finally show you part 2 of a video that we saw a couple of days ago. So, a parachutist jumps out of an airplane and free falls. They reach terminal speed and they maintain that speed for a while. They then open their parachute. They quickly reach a different terminal speed and descend to the ground. You good? Good, shut up. Sketch a speed versus time graph and explain for each section of the graph what's happening to the object. So we're going to go like this. And on the y-axis, we're going to put speed. Mr. Dewick, isn't speed S? No, speed is V without a vector. The vector would be velocity. And on the x-axis, we're going to put t time. Now, when I first gave this question, I said sketch a velocity time graph. Which way are you traveling when you jump out of an airplane, upwards or downwards? So my velocities would be negative. I didn't want to sketch everything down here below the x-axis, so I've changed everything to speed time graph. Okay, this is going to be a sketch, but we just want to see if we can get the shape. When I'm sitting on the edge of the airplane, before I jump, what's my vertical speed? 0. So there would be a stretch, I don't know how long, but there would be a stretch where the speed was 0 high, because the height is going to be the speed on the y-axis. Then I jump. Ah! What happens to my speed? Okay, I start to accelerate, but eventually, am I still accelerating? So it's going to increase, but here's my argument. I think at the beginning, I'm increasing the most, and as air resistance gets bigger and bigger and bigger and bigger, eventually I level off, and so this right here, that little section right there is free fall. When I jumped out of an airplane, I mentioned I jumped out of an airplane. When I jumped out of an airplane, I recall I was in free fall for about 30 seconds, not very long. You see why it kind of has to be curvy like that? You're speeding up the most at the beginning, but you slowly are accelerating less and less and less and less and less. Okay, I free fall for 30 seconds. What did I do next? Pull my parachute. What's going to happen to my speed? So I'm going to have a much lower height line. I think it looks like this. I think right away I decelerate the fastest. So it's going to be really quick deceleration. And then this section here is drifting down slowly with the parachute. Now here's where this graph is terrible. I recall that it took us 30 seconds of free fall, but about 10 minutes of drifting. So if I did this to scale, I would now continue this parachute line all the way out through my wall, all the way out over. I'm not going to draw this to scale because it should be a big amount of time. Emma, I'm going to say ignore that. So my scale is terrible. I'm going to get the shape right. I'm just about to hit the ground. Now what? Right when I hit the ground, what happens? What happens to my speed? Yeah? Oh, so you're saying, boom, I hit the ground, something like that? I always remember this graph because it sort of looks like an old VW bug from the side. And then I know I've got the right shape. Now, with you folks this year, I skipped a lot of the graphing that I've done in previous years. So if you found that terrifying and weird, don't freak out. I'm not going to be throwing a bunch of graphs at you. That was an intellectual exercise. What's your homework? Finish off lesson 2 and 3. Okay? You can also do number 1. Hannah, can you read me those 2 words right there that I just underlined? Oh, hang on. That comes later. What 2 words did I just underline? What force am I really talking about if I'm talking about a scale? Okay, so whenever you see that, you're going to think normal force. Okay, so number 1, absolutely. Number 2, elevator question. Number 3, elevator question. Number 3, I'm asking you to just come up with general equations by a free body diagram, no numbers. 4 is good. 5 is good. 6 is good. 7 is good. What does A want you to find? Using what? That's the fancy word for using D equals VIT plus a half AT squared, VF equals VI. Not using forces. You find A, but all of the old methods that we had to find an acceleration, Brian, are still fair game, not just your new one of A equals F over M. Okay? And then once you have the acceleration, I think you'll be able to find the force by going F equals M. A, your A from part A. I'm going to skip 8. I'm going to do 9. 10 is a conceptual question, assign that. 11 is a conceptual question, assign that. And 12 is a conceptual question, assign that. 13 and 14 are good as well. So I skipped a couple, but not that many. Sorry, you're going to get some homework for the long weekend. I just couldn't work my way around it.